Yo, can you hear me now? Can you hear me? All right, let's start. So today's session will be two pointers. All right, so we're gonna study two pointers. We're gonna read two pointers and yeah, let's begin. So introduction to two pointers. As the name implies, two pointer patterns refers to an algorithm that utilizes two pointers. Two pointers. What is pointer? Pointing means pointer. Meaning I don't know what pointer means, something along a T metal on a scale, indicate a figure or a position. So when we speak about two pointers, the pointers clearly indicate something. So each figures indicates kind of a position or a figure. So you gotta use that as a thing. So as the name All right, so this part, cool. So let's try two pointers. So what you understand what pointer means? So pointer, pointer means pointer is literally so let me give you the definition of pointer. So pointer is a long thin piece of metal on a scale or dial which moves to indicate a figure. So when we speak about two pointers, we got two things, all right? Two pointer or metal things. Right, so you have one pointer which is a metal, it moves to indicate a position. So when we speak about two pointers, we have two metals on a scale to indicate a figure or a position. So if we agree on this, now two pointers, we're going to use two pointers in a computer, all right? So we're going to use two pointers in a computer. In that case, we got to come up with a better definition of pointers. So now let's define, but you know, now in a computer, what is pointer? So pointer it's a variable that represents an index or position within a data structure like an array or linked list. It's an index or it represents an index or position within a data structure like an array or linked list. So many algorithms just use a single pointer to attain or keep track of a single element. Let's show you like an array. I hope you are at least you know what array means at this point. You gotta know an array. So array is basically a simple data structure. It's a contiguous data structure. So every index is like this. So this is a graphic representation of what array is. So array has a specific fixed size, and let's say this is an array. So whenever we see an array, each of index start with 0 and 1 memory location, 2 memory location, and the 3 memory location, and go on. So when we refer to an array and when we refer to pointer, in this case, it's a variable that represents that points to an index. So in this regard, this pointer is a variable. So first of all, it must be a variable. So pointer is variable. Okay. What is pointer? So pointer is a variable, but not just any kind of variable, but a variable that represents an index or position. So a variable, it's a variable that represents an index or a position. Good position in a data structure. This is very, very important definition. So this is pointer is a data structure, a variable literally representing. So you can say this is A. Right here we go. You have A, and you can say this is B. It's a point. It's a data structure. Okay, it's a data structure. So yo, it literally points to. So yo, see this? So now S A and represents A represents 2. So A represents 0 now, and B represent 1. Okay, A represent, and yeah, this is okay. Let me write it here. This is a variable that represents an index or a position. This is array, by the way. This is array. Okay, when it comes to a linked list, so you know a linked list has at least in linked list, at least you're gonna have this. This is linked list. This is, by the way, a single linked list. So at least they should have, okay, pointers. So this is a linked list. Okay, what? This is crazy. Anyways, what the hell? Oh, what the hell? So this is a linked list. So for pointer A, pointer can indicate, represent the first one, the first element, or the pointer could be indicates like the position. So it can represent the first element, and B can be represent the second one. So these are pointers. So I'm sure you get my point. So, but many algorithms just use single pointer to attain or keep track of a single element, and introducing like the second one, for example, is very important, because so you have two pointer, it means you can compare. Okay, whenever we have like first one things, you can compare with anything else, but when you have two pointers, man, you have a different world. You can track progresses. You can like compare two different positions. You can compare elements at those positions and like make comparison and make decision based on those comparisons. Like you have different world. So in many cases, like such comparisons are made using like two nested for loops, which takes kind of like difficult time, like O square time, quadratic times, because let's say like let's say you want to compare like the first elements and the elements with this position. So the option you have is like before two pointers, before two pointers, your only options are like nested loops. You know what I mean? Your only option is nested loops. So what you do is like you go through every element. So, but before this, before introducing two pointers, your only options, your before this, like before two pointers, your only option to compare two numbers is take that number, this position, and then go through it till you get here. For example, let's say you wanna compare this part with this part. Okay, these elements, you know what I mean? This is the first element, and let's say you wanna compare like this part. So this position and like this one. So your option is like first you go through over this, and now you find the first one, which is at the position one. Then once you get that, you compare over this and go through and find I. So you should have, it takes maximum of like O n square time, because you gotta compare every. But when it comes to two pointers, you just need to know this position you are in here, and like so like you got this, and oh, like you can compare it in constant time. That's the benefit you have when it comes to comparison. So like yeah, I mean, like we can do it into pointer strategy, and it can take up to O(n) time. So let's move on. Let me give you like the and for this case, like you can have like this. For example, like you can take literally this small. Now you compare this to. So you go through all over, and now you start again. You compare those elements. This is like crazy. Like I think you can see it clearly now. So this approach like doesn't take advantage of predictable dynamics, which exist like in the data structure. An example of data structure like with a dynamic predictability is like sorted array. So when we move a pointer in a sorted array, like we can predict whether the value being moved to is greater or smaller. For example, when moving a pointer to the right in ascending array guarantees we are moving to a value greater than or equal to the current one. All right, so you have sorted arrays. which means the prediction is if I is equals to, let's say, then like, so as you can see, data structure with predictable dynamics let us move pointer in a logical way. Like, for example, like you have, for example, you have like 1, 2, 3, 4, and you know if it is dynamic, like you have, all right, so well, 5, you see? So the prediction is, I hope you can hear me right now. Okay, so like this I, this is I. Okay, now let's continue. Instead of like I is here, we be pair, delete this, and I move on like, so the prediction is like, the prediction is like if nums I is equal to with this, what you do then? Then nums I plus 1 is literally greater than 2. So what do we mean by this? So this is a sorted array, and the array will give us predicted dynamics because we know this is sorted 1, and if the position is this, if nums I, this one, nums I, the value of this h is greater than 0, then like the, if this is greater than 0, so for example, the position is 2, 1, is it? No. Now it's 2. It is greater than, it is equals to 2. And we know that the next number, the next position is the next value is either greater than or equals to, is either greater or equals to 2. So this is, we can do this. And yeah, and so as you can see, like data structures with like predictable dynamics let us move pointers in a logical way. Like that's the advantage of taking advantage like this can improve time and space complexity, which will, okay, so two pointer strategy usually takes only O in time by eliminating the need for the nested for loops. There are three main strategies for using two pointers. The first one is inward traversal. There are three strategies. The first one is inward traversals, and two pointers algorithm usually takes only O in time by eliminating the need for the nested loops. As I told you here, you eliminate this when you compare. So you want to compare, so you can move whatever you want. Like for example, as I in this example, like let me put it here. So in two pointers, like you got two pointers, we're gonna now, so how can you use them? So you got these two pointers, like you have three kind of strategies how to use this. For first, like you can start from left and right of the array, and you can move inward, right? Like from here, like you can like this, and like from here, like you take like these shapes. Like you use inward, okay, till a specific position. Okay, now, so you can use these kind of strategies. Your pointers are two point. You start them like from the left and from the right endpoints. Then you move toward each other. So this method is called inward pointers. Okay, like you can literally use this as inward traversal. So this is inward traversal. So in this case, like what you do is literally you are here, the left part is here, and then you move it like this, one position at a time, like this, from here like this, each time, and from here. This is called inward pointer. So the pointer moves like toward the center, adjusting their position based on the comparison until a certain condition is met. So they meet each other. So here they meet until a certain condition are, so this until a certain condition is met. So they move or they cross each other. So this is ideal for the problem where we need compare elements from different end of data structures. This is very pretty good way to compare when we need to compare from different ends of the data structure. Okay, now are we on the same page? Like, oh man, this is like crazy. This is good. Okay, this is called inward traversal. Okay, we have like the second method, which is unidirectional, like the second method is like unidirectional traversal. In this approach, like both pointers start at the same end of the data structure, usually the beginning, and move in the same direction. So this pointer usually serve two different but supplementary purposes. A common application of this is when we want one pointer to find information, usually the right pointer, and another to keep track of information, usually the left pointer. So yeah, so let me show you, this is like unidirection. Let me write it here, unidirection pointers. All right, so for example, like, oh, this is crazy. Now let me copy this part. Pointer. Where is the pointer? Yo, where are the pointers? Let me draw it like this. So, yo, like, okay. This one is left pointer. Okay, instead of let me say this fast pointer and or right slow pointer. So what it does is like this. Yeah. So usually the fast pointer, so the fast pointer kind of check the conditions, and the left pointer kind of store informations. Okay. So we use the left pointer like to store informations, but the right pointer kind of check. But the left one, the faster one kind of used to check information, but the slower one is like to keep track of informations, you know, find information like the keep track of information. Okay, do we agree? All right, let's move on to the next traversal is stage traversal. So in this approach, we traverse with one pointer, and when it lands on an element that meets a certain condition, we traverse with the second pointer. Okay, similar to unidirectional traversal, both pointers serve different purposes. So where here the first pointer is used to search for something, okay, and once we found a second pointer finds additional information concerning the value at the first pointer. So we're going to discuss them later, but I will show you the examples. So they kind of serve a unidirectional traversal in some sense, but like they are kind of similar, but their purpose is different. So we traverse with one pointer. When it lands on an element that meets a certain condition, we traverse with the second pointer. And like then, similar to like both pointers like serve different purpose. So the first pointer is used to search for something. Once found, the second pointer finds additional information concerning the value at first pointer. So let me put it this way. So you have like this. Okay. Yo, can you hear me? All right. So like this is the first one. Okay, instead of saying this, let me change them over. So now let's say in the first sales, so like you find information, then this will let you keep your information. But here, what you do is like the first condition goes through, and then the second one, when you get some information, the second one will continue to find another information. Okay, yeah, this is how it works. This is called stage pointers. Okay, these are stage pointers. It's different from the previous one, like slow and fast pointers. So you have the slow one will keep information, and the fast will find information. But here, when the first find some part of the condition, the second will be checked also the other part. But I think this is clear, and we can look into them later. So where what is it good? Zen mode and right here. Okay, cool. Here is better. Now like when to use two pointers. Like for example, when should you use two pointers? So two-pointer algorithm usually require linear data structure, such as you can only use them on array or linked list. You can't use them in graph, okay? Because array and linked list are linear data structures. So you can use them in like, in graph, tree, like that. So, oh, so like the potentials of using the potential indicator of like to use two pointer is like if the problem asks for a pair of values, you can use them. So let's say like in a real world example, for example, Pearson, like let me find it in linked lists. Oh, I mean linked list. I say linked list. Dang, it's different. Yo, yo, man, it's literally different. Alright, so given to array, let's wait for me. Internal message, internal message, internal animal, yo, this is the problem. I hate white color. Let's change it. Okay, this is better. I think this is better. This is better. So the problem is, this is the problem. I'll give you time to read it. So the intuition is the brute force solution like involves checking like all possible pairs. Then this is done like using two nested loops. The outer loops traverse the array for the first element of the pair, and an inner loop traverse the rest of the array to find like the second element. Below, like I will show you like the code for this, and like yo, man, like you can like here show like the brute force way is oh boom, like you go through this first and then you check for the other pair like this. Now let me write the code. So define, so what is the problem? Twosome. So twosome, you have an array and target. Okay, so the array is, this is list of integers, and the target is just integer. We're gonna return bool. No, our list. So now let's know the links of the array first, or instead of R saying array, let's say nums. Okay, now we have nums. Okay, now let's move on. For I in the range of n, for j in range I plus 1, because we know I, and it doesn't make change. It doesn't make any difference if you like for example, you use 2 and 7 or 7 and 2. It doesn't make difference, all right? So like, and also we have only exactly one solution, so we can take this one and discard this. So for that reason I added this. Okay, so till n. So what you do is if nums I plus nums j is equal to target variable, what we will return is return I and j. What about else? So if you didn't get anything, you return the empty. All right, so this is, so the time complexity of this is like O square, because you used to check everything twice. Like this is nested loops. Your operation is O(n) square. Here you have how many operations here? Like you have n operation, maximum of n operations, and you will have like n operations as well. So in total, for every n operation, you will have n operations. So this is time complexity in worst case. But we want to do better, okay? So we want to do better. So how can we use this? So well, to make it easier, like to make the easier, like we can use 2 pointers, all right? So okay, now let's copy paste what you can do is literally you can use 2 pointers. From the right and the left. You don't have to move twice. Okay, you have the left one, you have the right one. So, and like this is sorted array. This is sorted, and the question also refers it because it is sorted array, I guess. If it is not, you can sort it. But so like if it is not sorted, this problem can be like difficult, a little difficult, but if it is sorted, like, but the question doesn't indicate that it must be sorted. So we start by sorting the problem. So for example, in this case, the problem is not sorted. So like it's not sorted. So the first thing we gotta do is sort the array. Sort it. The first thing we will do is sort the array, and like the second, then after we sort it, we can use pointers. So let's go. So like let's move on here. This already sorted, so if sorted we don't have to use anything. But for this case, like we check the right one and the left one. So this 2 plus this, so it's less. It's what's the value? value is like 17. 17 is greater than this. So we know by default that when we sort it, we really understand that these two numbers, like the first one, this one, and this is, so the second one is greater than the first. All right, we know this. If we sort it in an ascending order, we know this is less than the second. So from this, so this pointer, like the right pointer, right, and the left. So we understand the right is greater than the left. So since it is their sum is less than this, we minus it here. So let's define a function. And you have nums, you have like target. So like sorted, you can sort it like this. Right now, the left child and less length of nums, and the left child is start with 0, and the right child must start with n, the length -1, because -1 is the end of it. So while we will do it like left is less than right, as long as if they cross each other, we will terminate it. So if so, like if nums left plus nums right is like greater than target. If it is greater than the target, which means beyond the target, so you gotta shrink the right one, because the right is always greater than the left. So left, you will write -1. And if nums left plus nums right, you don't have to check this. Elif right is less than the target. Oh, now the left one will else return this left and right. If we don't have anything, return this. You empty. I believe this is a solution. I'm not sure, yeah. But this is but as I told you before, the use case of this problem is you gotta have to have like when the inputs are predictable dynamic. This is very, very important. And this problem, we don't have predictable dynamics like in this example. Where is the example? The second example. In this example, we can't. This is not predictable dynamics, so we make one for ourselves. Okay, because there is no prediction, ups and downs. So like to be in this problem, like you gotta like this. If it is in this way, like you don't know. Or like this, you don't know. Okay, but what you want to do, what you want is like this. Like this is great because you know it's increasing. Or like this, or like this is decreasing. Yeah, you know this is decreasing, that's increasing. But in this case, it ups, it increase. You may know, but somehow it falls, decrease. You don't know yet. So to avoid these situations, we use sorted. We sorted it first. That's why. Well, one of my problem, I find it finally, but we gotta know like whenever we sort it, like if we sort this problem, like there is a dead end because oh now I realized it. Bro, I forget. But you know this doesn't retain the original index. So all we wanna do is to return the original index, but that doesn't work. Man, this is crazy because we gotta retain the original. Yo, because when we sort the so when we sort it, bro, that's different ball game. All right, we gotta like we haven't used, so that's different. That's different. Yeah, man. Yo, like so we can use so we can directly use two pointers. Like we gotta like somehow tweak the problem because this only work if it is sorted already. So the given inputs sorted input, okay? We don't have to sort it. If we sort it, we will lose the index position. Like, you know what I mean? The original index will be lost. So this is like for a problem which is given to already sorted. But if it's not, like we gotta create something out of this. We gotta maintain the index somehow first. So that way, yo man, now like, so there are problems. There are problems like, there are some problems here and there, like we will check them out later or some other times. So like palindrome or largest container, we will return palindrome largest container. See you tomorrow. See you tomorrow. We're gonna solve palindrome and largest container and fix this situation. All right, and triple. Before that, two sum, and then triple sum. So tomorrow we're gonna solve these problems. So see you tomorrow. Yeah.